So you know that circle thing, right? The thing where if you take any circle, and I mean literally any circle, from a dinner plate to the sun, and you divide how far it is around by how far it is across, you get the same number every single time. That number is about 3.14159, and it just keeps going forever. We call it pi now, but people have been obsessed with this number for almost 4,000 years. This is the story of how we went from ancient accountants in Babylon eyeballing circles to computers calculating trillions of digits. And trust me, this story gets weird. Okay, so picture this. It's about 2500 BC in ancient Mesopotamia. You're in Babylon, which is basically the Silicon Valley of the ancient world. They've got writing, they've got a number system, they've got the abacus, which back then was like having the latest iPhone, and they're dealing with this huge problem. They need to figure out how much grain fits in cylindrical storage containers. Because here's the thing, if you're running an empire, you need to collect taxes. And to collect taxes, you need to measure stuff. And a lot of that stuff involves circles. Round grain bins, circular water tanks, wheels on carts. Every time you're dealing with a circle, you run into this ratio. The Babylonians came up with 3.125, which honestly, for just measuring physical circles and averaging the results, that's pretty good. They were within about 1% of the actual value, and they didn't even have rulers that measured anything precisely. They were just using ropes and doing their best. Then, about 500 years later, you've got Egyptian scribes dealing with the same problem, but they're coming at it from a different angle. There's this surviving document called the Rind Papyrus from around 1650 BC, and it's basically an ancient math textbook. Some scribe named Ames wrote out 84 math problems, and buried in there is their method for calculating the area of a circle. Their approach was kind of clever. They said, okay, take your circle's diameter, chop off 1/9 of it, then square what's left. That gave them a value of about 3.16. Again, not exact, but close enough to build pyramids that are still standing today. Here's what blows my mind about this early stuff. These people had no concept of what they were really dealing with. They didn't know this number went on forever. They didn't know it was the same for every circle. They just knew that when they measured circles, they kept getting roughly the same answer, and that was useful enough. Meanwhile, over in India, around 800 BC, religious scholars were trying to standardize altar construction. They needed altars that were different shapes, circles, squares, semicircles, but had the same area. So they're out there with ropes and bricks trying to square the circle, and they got to about 3.138. All of these civilizations independently figured out that circles have this special ratio, and they all got within a few percent of the real value, but none of them really understood what they were dealing with. They thought it was just a practical measurement thing. Then, around 250 BC, this Greek mathematician named Archimedes shows up and changes everything. Archimedes is one of those people who was just on a different level. This guy calculated the volume of a sphere, figured out the principle of buoyancy, invented war machines to defend his city from the Romans. He was doing the work of like 5 modern mathematicians and engineers combined. But what he did for pi was create the first actual mathematical method to calculate it, not just measure it. and his approach was brilliant in its simplicity. Here's what he did. He drew a circle, then drew a polygon inside it where all the corners just touched the circle. This is called an inscribed polygon. Then he drew another polygon outside the circle where all the sides just touched it. That's a circumscribed polygon. Now, the circumference of the circle has to be somewhere between the perimeters of these two polygons, right? The inside one is too small, the outside one is too big, but the real circumference is trapped in the middle. Then Archimedes did something clever. He started with a hexagon, 6 sides, calculated the perimeters, not close enough. So he doubled it to 12 sides, then 24, then 48, then 96. By the time he got to 96 sides, his polygons looked almost exactly like a circle, and he could prove mathematically that pi was between 3 and 10/70 and 3 and 1/7. In modern decimal notation, that's between 3.1408 and 3.1429. This blew away everything that came before. Not because it was so much more accurate, though it was, but because it was a method. You could keep going. You could double the sides again, and again, and again, and you'd get closer, closer to the real value. This is called the method of exhaustion. You're exhausting all the space between your polygons and the circle, and it worked. For over 1,000 years, this was how people calculated pi. Archimedes got so close with just 96 sides that he basically nailed it to 4 decimal places using nothing but geometry and logic. No calculators, no computers, just thinking really hard about shapes. The method was so good that people sometimes call pi Archimedes' constant. Even today, when you see people explaining pi, they often start with this polygon approach because it just makes sense. But then things got quiet in Europe. The Roman Empire fell, the library at Alexandria burned, and a lot of Greek mathematical knowledge just kind of disappeared. For centuries, not much happened in the Western world when it came to pi. But while Europe was going through the Dark Ages, China was having its own mathematical renaissance. Around 265 AD, this mathematician named Liu Hui looked at Archimedes' method and thought, you know what, I can make this better. He created an algorithm that was even more efficient. Instead of tracking the perimeters of polygons, he tracked the areas, which turned out to make the math easier. Liu Hui got pi accurate to 5 decimal places using a polygon with nearly 200 sides. But the really cool thing is what he did next. He realized that the error in his calculation was decreasing in a predictable pattern, roughly by a factor of 4 every time he doubled the sides. So he worked out a shortcut to jump ahead without having to actually do all the calculations. This is one of the first examples in history of what we'd now call convergence acceleration. Then, about 200 years later, another Chinese mathematician named Zhu Chongji took Liu Hui's method and just ran with it. We're talking around 480 AD here. Zhu used a polygon with 24,576 sides. Let me say that again. 24,000 sides. Remember, this is all being done with counting rods, basically wooden sticks laid out in patterns. No abacus, no calculator, just sticks and an insane amount of patience. The calculations involved hundreds of square root extractions, all done by hand, each one accurate to at least 9 decimal places, and Zhu got pi correct to 7 decimal places. 3.1415926 to 3.1415927. That record stood for nearly 900 years. Nobody in the world would match it until the 1400s. But Zhu also did something else really clever. He came up with two fractional approximations. The approximate ratio was 22/7, which people still use today. But then he found the close ratio 355/113. That fraction, 355/113, is remarkably accurate. It's correct to 6 decimal places. You don't get a better fraction until you use a denominator with 5 digits, and Zhu found it in the 5th century using nothing but polygons and sticks. A Japanese mathematician later looked at this and basically said, "Look, the Greeks had 22/7 thanks to Archimedes, but this 355/113 thing, nobody in Greece, India, or Arabia had this. The Chinese had it 1,000 years before Europe stumbled on it." That's why he argued it should be called Zhu's fraction. Meanwhile, something really interesting was happening in southern India that nobody in the West knew about for centuries. Around 1340 to 1425, there was this mathematician named Madhava working in Kerala in southern India. And Madhava did something that wouldn't be done in Europe for another 300 years. He figured out how to calculate pi using infinite series. Here's what that means. You know how you can add 1/2 plus 1/4 plus 1/8 plus 1/16 and keep going forever? If you do that infinitely, you get exactly 1, not approximately 1, exactly 1. Madhava realized you could do the same thing with pi. He came up with this formula. Pi divided by 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, on and on forever. Now, this particular series is really slow to converge. You'd need thousands of terms to get decent accuracy. But Madhava found better series too, much faster ones. Using these series, Madhava calculated pi to 11 decimal places in the 1400s, without calculus. That's about 350 years before Newton and Leibniz invented calculus. He also found infinite series for sine, cosine, and arctangent, stuff that would later be called Taylor series when European mathematicians rediscovered them. Madhava even understood the error terms. He knew how to estimate how wrong his approximations were. This work was documented by his students and successors in the Kerala School of Mathematics. But here's the sad part. It mostly stayed in Kerala, written in Sanskrit and Malayalam on palm leaf manuscripts. This knowledge didn't spread to Europe. So when James Gregory found the arctangent series in 1671 and Leibniz found it in 1673, they had no idea a guy in India had beaten them to it by 300 years. Modern historians sometimes call these the Madhava-Gregory series or the Madhava-Leibniz series, to give credit where it's due. But for centuries, Europeans didn't know about this stuff because there just wasn't good contact between Kerala and Europe at the time. There's this tantalizing question historians argue about: could some of this knowledge have leaked to Europe through Jesuit missionaries and traders? The port of Cochin, near where Madhava worked, was a major trading hub. Europeans were definitely there by the early 1500s. It's possible some mathematical ideas traveled along the spice routes, but we have no direct evidence, so it remains a mystery. All right, so eventually Europe comes out of the medieval period and things start picking up again. It's the 1600s and calculus is about to be invented. In 1655, an English mathematician named John Wallis published this wild infinite product formula for pi. Instead of adding fractions, you're multiplying them. It looked completely different from anything that came before. Then Newton and Leibniz independently invented calculus in the 1660s, and suddenly you could do crazy things with infinite series. Newton used an arcsine series to calculate pi to 15 digits, then later wrote that he was ashamed to tell you to how many figures I carried these computations, because he basically kept going just for fun when he had nothing else to do. In 1671, James Gregory found the arctangent series. In 1673, Leibniz independently discovered it. When Leibniz announced his result, other mathematicians went wild. His mentor Huygens told him, "This remarkable property of the circle will be celebrated among mathematicians forever." Even Newton praised it. The thing about the Leibniz series is that it's beautiful to look at. Pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7. It's so simple and elegant, but it's terrible for actually calculating pi. To get just 50 accurate digits, you'd need to calculate so many terms that, as Euler later put it, you'd have to work almost forever. But now people knew you could use infinite series, so they started finding better ones. In 1706, a guy named John Maschin came up with this brilliant trick. Instead of using the arctangent of 1, which gives you that slow Leibniz series, he used the arctangent of 1/5 and the arctangent of 1 over 239. When you combine those in just the right way, you get pi, but the series converges way faster. Maschin used this to calculate pi to 100 digits by hand. This was the first time anyone had ever broken through the 100-digit barrier, and Maschin did it with a quill, pen, and paper. Now, here's a fun detail. That same year, 1706, a Welsh mathematician named William Jones did something that seems minor but ended up being huge. He started using the Greek letter pi to represent this number. Jones picked pi because it's the first letter of the Greek word perimetros, meaning perimeter or periphery. Before this, mathematicians used all kinds of different notations. They'd write the ratio of the circumference to the diameter, or use random letters like C or P. It was a mess. Jones's notation didn't catch on immediately, but then in 1737, the most influential mathematician of the era, Leonhard Euler, started using it. And when Euler does something, everyone copies him. By the mid-1700s, pi was the standard symbol worldwide. Euler himself was an absolute machine when it came to calculations. He used Maschin-like formulas to calculate 20 digits of pi in 1 hour. 1 hour, most of which was probably spent double-checking his arithmetic. Throughout the 17 and 1800s, mathematicians kept pushing the digit count higher and higher. By 1873, a guy named William Shanks had calculated 707 digits by hand. Unfortunately, later, mathematicians found an error at digit 528, so only the first 527 digits were actually correct. But still, 527 digits with just pen and paper, that's dedication. But alongside all this calculation work, people were starting to ask deeper questions about pi itself. What kind of number is this, really? In 1761, Johann Heinrich Lambert proved something important. Pi is irrational. That means you can't write it as a simple fraction. It's not 3/1. It's not 22/7. It's not 355/113. There's no fraction, no matter how big the numbers get, that exactly equals pi. Lambert used continued fractions to prove this, which is this whole complicated thing where you write a number as an integer plus a fraction, but the denominator of that fraction is another integer plus a fraction, and so on forever. It's actually pretty elegant once you see it, but the proof is not easy. But even knowing pi was irrational, people wondered, could it still be the solution to some polynomial equation with rational coefficients? Like, could it be the solution to something like x squared equals 10, or some more complicated polynomial? Numbers that can't be solutions to any polynomial with rational coefficients are called transcendental. And in 1882, a German mathematician named Ferdinand von Lindemann proved that pi is transcendental. This was huge, because it meant something people had wondered about for 2,000 years, since ancient Greece was finally settled. You cannot square the circle with just a compass and straight edge. It's mathematically impossible. See, the ancient Greeks were obsessed with three construction problems: trisecting an arbitrary angle, doubling the cube, and squaring the circle, all using just a compass and a straight edge, no markings, no measuring. Squaring the circle means constructing a square with the same area as a given circle. The problem is, to do that, you'd need to construct a length of the square root of pi, and you can only construct lengths that are solutions to certain polynomial equations. If pi is transcendental, then the square root of pi is transcendental, and you can't construct it. Problem impossible. Lindemann's proof used some advanced techniques from complex analysis and number theory. He showed that if alpha is any non-zero algebraic number, then e to the power of alpha is transcendental. Then, using Euler's famous formula, e to the I pi equals -1, he proved that if pi were algebraic, you'd get a contradiction. So pi must be transcendental. This was one of those proofs that closed a chapter in mathematics that had been open for millennia. After Lindemann, we knew exactly what kind of number pi was: irrational, transcendental, going on forever with no pattern, and impossible to construct with classical Greek tools. Now let's jump to the modern era, because things get really interesting when computers enter the picture. The first computer calculation of pi happened in 1949. The ENIAC, one of the first electronic computers, calculated 2,037 digits in 70 hours. That smashed William Shanks' record, though honestly, Shanks might have been relieved to know a computer could do in 3 days what took him years. But the real breakthrough came in 1987, when two Ukrainian-American mathematicians, David and Gregory Chudnovsky, came up with a new formula. The Chudnovsky formula is based on work by the Indian mathematician Ramanujan, who was this absolute genius from the early 1900s. Ramanujan had found these crazy formulas for pi that converged ridiculously fast. The Chudnovsky brothers took Ramanujan's ideas and optimized them even further. Here's the thing about the Chudnovsky algorithm. Each term you calculate gives you about 14 new correct digits of pi. Compare that to the Leibniz series, where you might need thousands of terms to get even a few digits, and you can see why this was revolutionary. The formula itself looks completely insane. It's got factorials and huge numbers like 600, 40,000, 320 cubed, and all these other terms that look like someone just made them up. But it comes from deep mathematics involving elliptic curves and modular functions. Ramanujan somehow intuited this stuff 100 years ago without modern mathematical tools, which is part of why people call him a genius. The Chodnovsky algorithm became the go-to method for breaking pi digit records. In 1989, the Chodnovsky brothers themselves used it to calculate over 1 billion digits on a homemade supercomputer they built in Gregory's apartment. Gregory had a medical condition that kept him homebound, so they just built the computer there. This thing was a beast, multiple processors, hard drives everywhere, and they used it to push the boundaries of what was possible. From there, the records just started tumbling. 2009, 2.7 trillion digits. 2011, 10 trillion. 2016, 22 trillion. 2019, 31 trillion. In 2020, someone hit 50 trillion digits. Then 62 trillion in 2021. 100 trillion in 2022. 202 trillion in 2024. And as of April 2025, the record stands at 300 trillion digits. 300 trillion. That computation took over 226 days, nearly 8 months of a computer just grinding away, using the Chodnovsky algorithm and a program called Y-Cruncher. The person who wrote Y-Cruncher, Alexander Yi, started it as a high school project. Now it's the standard tool for world record pi calculations. That's pretty cool. At this point, the bottleneck isn't even the calculation itself. Modern CPUs can handle the arithmetic. The problem is memory and storage. To calculate 200 trillion digits, you need about a petabyte of temporary storage space. The recent record attempts used dozens of high-capacity solid-state drives just to handle all the intermediate results. So why do we keep calculating more and more digits? I mean, NASA uses like 15 digits of pi for interplanetary navigation. That's enough to calculate the circumference of the observable universe to within the width of a hydrogen atom. What's the point of 300 trillion? Part of it is just because we can. It's a benchmark for computational capability. Breaking a pi record shows off your hardware, your software optimization, and your algorithm implementation. But there's also real science here. One thing mathematicians look for is patterns in the digits. So far, pi passes all the statistical tests for randomness. The digits appear to be evenly distributed. You get about the same number of zeros, ones, twos, all the way through nines. There's no pattern anyone has found. But we keep checking because if there were a pattern, that would tell us something deep about the nature of circles and the universe itself. The fact that pi appears random is actually meaningful. Pi digits are also used as a source of pseudo-random numbers in certain applications. If you need a long string of random-seeming numbers, pi's digits work pretty well, though cryptographers prefer other methods for security-critical stuff. There's also this connection to physics that's emerged. Recently, physicists found that formulas Ramanujan developed 100 years ago to calculate pi are deeply connected to modern theories about quantum mechanics, turbulence, and even black holes. These mathematical structures keep showing up in completely different areas of physics. As one physicist put it, in any piece of beautiful mathematics, you almost always find that there is a physical system which actually mirrors the mathematics. Ramanujan might have thought he was just doing pure math, but he was also, without knowing it, exploring the mathematics of black holes and turbulence and all sorts of physical phenomena. Let's talk about where pi shows up, because it's way more than just circles. Obviously, anything involving circles uses pi: wheels, gears, cylinders, spheres. If you're an engineer designing anything round, pi is your constant companion. But pi shows up in places that have nothing to do with circles. It's in the Gaussian distribution, the bell curve, which is used in statistics everywhere. It's in the Heisenberg uncertainty principle in quantum mechanics. It's in the equations describing electrical circuits and the orbits of planets. Pi appears in the formula for the period of a pendulum. It's in the equations for electromagnetic waves. It shows up in the solutions to certain differential equations that describe everything from heat flow to the diffusion of chemicals. There's a famous probability problem called the Buffon's needle problem, where you drop a needle on lined paper and the probability it crosses a line involves pi. Even though we're talking about straight lines and needles, somehow pi shows up. Pi appears in the Riemann zeta function, which is connected to prime numbers, and prime numbers are, again, nothing to do with circles. Yet, there it is. Some of these appearances make sense when you dig into the mathematics. A lot of them involve integration over circles or periodic functions, but some of them feel almost spooky. Why does this number about circles keep showing up in probability, quantum mechanics, number theory? The answer is that pi is more than just a number about circles. It's connected to fundamental properties of space, waves, periodicity, and symmetry. It's baked into the structure of mathematics itself. Here's a fun fact that people always bring up. There was almost a time when pi was legally defined as the wrong value. In 1897, an amateur mathematician in Indiana convinced a state representative to introduce a bill that would legally set pi to various incorrect values, including 3.2. The bill was about a method to square the circle, which, as we now know, is impossible. The Indiana House of Representatives actually passed this bill. It got sent to the Senate, where, fortunately, a mathematics professor from Purdue happened to be visiting the state capitol. He saw what was happening and convinced the senators that you can't change mathematical constants by legislation. The Senate postponed the bill indefinitely, which is political speak for "we're pretending this never happened." But for a brief moment, Indiana almost legally defined pi incorrectly. This bill is now famous as a warning about the dangers of scientific illiteracy in government. You can't legislate reality. Numbers don't care about laws. Though imagine the chaos if it had passed. Sorry, your building fell down because we used Indiana pi for the calculations. There's this other modern thing with pi that I find hilarious. We've got Pi Day, March 14th, written as 3/14 in American date format. People eat pie, make pie jokes, memorize digits. The obsession with memorizing pi digits is its own weird subculture. The world record is over 70,000 digits memorized by a guy who spent years training his memory. Why? Honestly, I don't know. But people do it. There are competitions, techniques, memory palaces where you convert digits to images and construct mental journeys through imaginary locations. It's simultaneously impressive and completely pointless. There's also this thing where people find patterns in pi digits that aren't really patterns. Like, look, at position 762, you get 6 nines in a row. This is called the Feynman point after physicist Richard Feynman, though there's no actual connection to Feynman. It's just a thing that happens. People get excited about finding their birthday in pi, or their phone number, or their social security number. And yeah, you can find pretty much any sequence eventually because pi goes on forever. But mathematically, that's not really meaningful. Though I will say, the fact that we can check whether specific sequences appear in pi is kind of cool. There are websites where you can search for any sequence of digits and it'll tell you where it first appears in pi, if at all in the digits we've calculated so far. So where does all this leave us? We've been chasing this number for 4,000 years. From Babylonian accountants eyeballing circles to supercomputers calculating 300 trillion digits. We've proved it's irrational and transcendental. We've found infinite series and products and algorithms that converge faster and faster. We've connected it to physics and statistics and number theory and basically every branch of mathematics. And after all that, pi still holds mysteries. We don't know if pi is a normal number, meaning every possible finite sequence of digits appears in it with equal frequency. It sure looks normal based on statistical tests, but we haven't proven it. We don't know why Ramanujan's formulas connect to black holes and turbulence. We're still discovering new places where pi appears unexpectedly. And we keep calculating more digits, not because we need them for any practical purpose, but because the journey of pushing boundaries teaches us things about computation, about algorithms, about the nature of numbers themselves. That's what makes pi fascinating. It's not just a number. It's a constant that's been a companion to human civilization from the very beginning. Every culture that did mathematics stumbled upon it eventually. Everyone who studied circles deeply enough found themselves face to face with this infinite, non-repeating decimal that somehow captures something essential about space itself. From Archimedes sweating over his 96-sided polygon, to Zhu Chengji laying out 24,000 counting rods, to Madhava discovering infinite series, to the Chudinovskys building a supercomputer in an apartment to calculate billions of digits. They're all part of the same story. The story of humanity trying to understand the mathematical structure of reality, one circle at a time. And that number, 3.141592653589793233846, it just keeps going forever. And we'll keep chasing it, because that's what we do. We see a pattern, we see a mystery, we see something beautiful in the mathematics of the universe, and we can't help but dig deeper, even if it takes 4,000 years. So next time you see a circle, or you see that pi symbol, remember, you're looking at something that's connected humanity across cultures and millennia. A number so simple a child can understand what it means, yet so deep we're still exploring it with the most powerful computers we can build. Now, let me tell you more about some of the fascinating details that got glossed over in that whirlwind tour. Let's go back to Archimedes for a moment, because his story is worth dwelling on. This guy was living in Syracuse, in Sicily, during a time when Rome was expanding aggressively. Syracuse was a Greek colony, rich and powerful, but Rome wanted it. Archimedes was in his 70s when the Romans besieged Syracuse, and according to ancient accounts, he personally designed war machines that terrorized the Roman fleet. Giant cranes that would lift ships out of the water and smash them. Mirrors that focus sunlight to set ships on fire. Though historians debate whether that last one is true or legend. The Roman general Marcellus apparently said that Archimedes was using his ships for a game, like targets in a drinking party. The siege lasted 3 years because of Archimedes' defenses. When the Romans finally broke through, a soldier found Archimedes drawing geometric diagrams in the sand. According to the story, Archimedes told the soldier not to disturb his circles. The soldier, probably not in the mood for mathematics lessons after a 3-year siege, killed him on the spot. Marcellus was reportedly furious about this and gave Archimedes an honorable burial. On his tomb, they inscribed a sphere inscribed in a cylinder, because Archimedes considered his proof about the volume of a sphere to be his greatest achievement. He proved that if you put a sphere perfectly inside a cylinder, the sphere's volume is exactly 2/3 the cylinder's volume, and their surface areas have the same ratio. This is a guy who changed mathematics forever, defended his city for 3 years using physics and engineering, and died drawing circles in the sand. And 2,000 years later, we're still using his methods to understand pi. Let's talk more about those Chinese mathematicians too, because their story deserves more space. Liu Hui was working in the 3rd century AD during the Three Kingdoms period in China. If you know the romance of the Three Kingdoms, that's the setting. It was a time of war and chaos, but also incredible cultural and intellectual activity. Liu Hui wrote a commentary on a much older mathematical text called The 9 Chapters on the Mathematical Art. This was China's version of Euclid's Elements, the foundational math textbook that everyone studied. But Liu Hui didn't just comment on the old text. He added his own insights, proved things that had been stated without proof, and developed new methods. His work on pi was part of this larger project of making Chinese mathematics more rigorous. What's cool about Liu Hui's approach is that he understood limits in a way that was pretty sophisticated for his time. He wrote something like, "The more you cut, the smaller the loss. Cut again and again until you can't cut anymore." And it matches the circle exactly, with no loss. That's essentially describing the limit process that wouldn't be formalized in calculus until Newton and Leibniz in the 1600s. Liu Hui got the intuition right, even if he didn't have the formal mathematical framework we use now. Now, Su Chongji, working about 200 years later, was also doing a lot more than just calculating pi. He reformed the calendar, invented an early version of the south-pointing chariot, which is like a mechanical compass that used differential gears, and designed paddle wheel boats. But his pi calculation is what really stands out, because think about what he was doing. A polygon with 24,000 sides, each calculation building on the previous one, with wooden counting rods. The counting rod system was actually pretty sophisticated. You could represent numbers efficiently, do addition and subtraction relatively easily, even handle some multiplication and division. But square roots? Square roots of numbers with multiple decimal places? That's brutal. And Zhu did hundreds of these calculations. It would have taken months, maybe years of work. And he kept all the intermediate results organized well enough that the final answer was correct to 7 decimal places. There's a reason this record stood for almost 900 years. Nobody else had both the method and the patience to match it. European mathematicians in the Renaissance eventually caught up, but Zhu had beaten them to it by a millennium. Let's dive deeper into that Kerala school of mathematics, because it's one of the most interesting stories in the history of math, and most people have never heard of it. Madhava was working in what's now Kerala state in southern India, along the Malabar coast. This was a major center for the spice trade, and it was relatively wealthy and cosmopolitan. Different religions and cultures mixed. You had Hindus, Muslims, Christians, Jews, all living and trading together. The Kerala school that Madhava founded lasted for about 300 years, from the 1400s to the 1700s. There were at least 6 major mathematicians in this tradition, all building on each other's work. After Madhava, you had Parameshvara, who made detailed astronomical observations and wrote commentaries on Madhava's work. Then Nilakanta Somayaji, who attributed many results directly to Madhava. Then Jayastadeva, who around 1530 wrote the Yuktibhasa, a book that actually explained the proofs of these infinite series in detail, not just stating results but showing how to derive them. Here's what makes this even more remarkable. European mathematicians didn't publish proofs of these same series until the late 1600s. And they weren't as complete as Jayastadeva's explanations from 1530. The Yuktibhasa was written in Malayalam, not Sanskrit, which means it was aimed at a broader audience, not just elite scholars. It's essentially a complete textbook on mathematical analysis, covering infinite series, trigonometry, calculus concepts, all explained step by step. For centuries, this knowledge just sat there in Kerala on palm leaf manuscripts, in libraries and family collections. Some people knew about it locally, but it didn't spread internationally. Then, in the 1940s and 50s, historians of mathematics started really digging into Indian mathematical texts. They found these manuscripts and realized, wait, this is calculus. This is infinite series. This predates Newton by centuries. There was this scholar named C.T. Rajagopal who, along with others, started translating these texts and writing about them in English. Suddenly, the mathematical world realized that this whole school of advanced mathematics had existed, done groundbreaking work, and been essentially forgotten. Now historians debate how much influence this might have had on European mathematics. Jesuit missionaries were in Kerala by the early 1500s. Traders were passing through constantly. Is it possible that some of these ideas leaked out and influenced European mathematicians? We don't have smoking gun evidence, but it's at least plausible that some knowledge traveled along the trade routes. Mathematics doesn't exist in a vacuum. People talk, share ideas, show each other their work. Maybe someone saw a manuscript. Maybe a sailor or trader carried some mathematical ideas back to Europe without fully understanding them. Or maybe Newton, Leibniz, and Gregory really did discover everything independently. Parallel invention happens in mathematics all the time. When the time is right, when certain prerequisite ideas are in place, smart people in different places often discover the same things. Either way, what Madhava and the Kerala school accomplished is legitimately impressive. They pioneered concepts that we now consider foundations of calculus, and they did it first. Now let's talk about the 17 and 1800s in Europe, because this is when things really start picking up speed. By the early 1700s, mathematicians had this new tool, calculus, and they were finding infinite series left and right. It was like the gold rush of mathematics. Everyone was looking for new series, new formulas, new ways to calculate things. The Leibniz series, pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7, became almost famous among mathematicians, even though it's terrible for practical calculation. It was just so beautiful and unexpected. Because here's the thing, why should pi be connected to the sum of the reciprocals of odd numbers? what do circles have to do with adding 1 minus a third plus a fifth? It's not obvious, but when you derive it from the arctangent series, it falls out naturally. That's the kind of thing that makes mathematicians go, whoa. John Machin's formula was a breakthrough because it was actually useful. He realized that arctangent of 1/5 converges much faster than arctangent of 1, and by cleverly combining arctangent of 1/5 and arctangent of 1 over 239, he could get pi while only needing to calculate relatively few terms. This became the basis for Machin-like formulas, a whole family of similar approaches. Throughout the 17 and 1800s, mathematicians kept finding new combinations of arctangent terms that converged even faster. It became a bit of a sport. Leonhard Euler shows up in this period, and Euler is just everywhere in mathematics. He published over 800 papers and books during his lifetime, and he kept working even after he went blind. His secretary would write down what Euler dictated, and Euler could keep complex equations in his head. Euler didn't just popularize the pi symbol. He found new formulas, proved results about pi, connected pi to e and I in his famous formula, e to the I pi equals -1. This formula is sometimes called the most beautiful equation in mathematics because it connects 5 of the most important constants, e, I, pi, 1, and 0 in one simple equation. Euler also proved that E is irrational, laying groundwork that would eventually help mathematicians prove pi is irrational too. Then there's Lambert in 1761, proving pi is irrational using continued fractions. Continued fractions are this beautiful idea where you write a number as an integer plus a fraction, but the denominator of that fraction is another integer plus a fraction, and so on. For rational numbers, this process terminates. For irrational numbers, it goes on forever. But it gives you really good approximations. The partial fractions you get by cutting off the continued fraction at various points are the best possible rational approximations for the size of the numbers involved. Lambert showed that pi's continued fraction goes on forever in a way that proves it can't be rational. The proof is elegant, but not easy to follow without some background in number theory. Let's talk about William Shanks, because his story is both impressive and a cautionary tale. Shanks spent years calculating pi by hand. Years. He was a British mathematician in the mid-1800s, and he was absolutely meticulous. He checked his work multiple times. He used Machin's formula and carefully worked through all the arithmetic. By 1873, he had calculated 707 digits. At the time, this was by far the world record. Shanks published his results, and they stood for decades as the most accurate value of pi known to humanity. Then, in the 1940s, D.F. Ferguson decided to double-check Shanks' work. Ferguson also calculated pi by hand, using a mechanical desk calculator to help with the arithmetic, and he found an error. At digit 528, Shanks had made a mistake. Everything after that was wrong. Shanks got 527 digits correct, which is still impressive. But that means he spent years calculating digits that were completely wrong, and he never knew it. This is why computers are so valuable in mathematics. Humans make mistakes, even careful, meticulous humans. Shanks probably transposed 2 numbers somewhere or made an arithmetic error that propagated through all his subsequent calculations. And because the calculations were so tedious, he never caught it even though he checked his work. When computers came along, one of the first things mathematicians did was recalculate pi to make sure we had it right. And thank goodness, because we'd been working with incorrect digits for 70 years. Now, the proof that pi is transcendental deserves more discussion because it's actually a pretty big deal mathematically. First, what's an algebraic number? It's any number that's a solution to a polynomial equation with rational coefficients. So the square root of 2 is algebraic because it's a solution to x squared equals 2. The golden ratio is algebraic. Even complex numbers can be algebraic if they solve the right kind of polynomial. Most numbers you encounter in everyday life are algebraic. Even most irrational numbers are algebraic. So when we say a number is transcendental, we're saying it's not just irrational. It's irrational in this very specific, profound way where it can't be captured by any polynomial equation. Hermite proved in 1873 that E is transcendental. His proof was clever but super technical. Then Lindemann in 1882 extended the method to prove pi is transcendental. The key insight is Euler's formula, e to the I pi equals -1. If pi were algebraic, then I pi would be algebraic too, because algebraic numbers are closed under multiplication. If you multiply an algebraic number by another algebraic number, you get an algebraic number. But Hermite had already proved that e to the power of any non-zero algebraic number is transcendental. So e to the I pi should be transcendental. But e to the I pi equals -1, which is definitely not transcendental. It's rational. That's a contradiction. So our assumption must be wrong. I pi can't be algebraic. Therefore, pi is transcendental. The proof has been simplified and refined over the years, but that's the essence of it. It's a beautiful argument. Use one result to bootstrap another and catch a contradiction. What this immediately tells you is that you can't square the circle, because any number you can construct with compass and straightedge is algebraic. You're essentially solving a sequence of quadratic equations every time you use those tools. So, if pi is transcendental, you can't construct the square root of pi, which is what you'd need to square the circle. This closed a problem that had been open since ancient Greece. For over 2,000 years, people tried to square the circle. Countless attempts, countless claimed solutions, all wrong. Lindemann proved it was impossible. Yet even after Lindemann's proof, people kept trying. Even today, occasionally someone claims they've squared the circle. They're wrong, of course. You can't argue with mathematical proof, but people try anyway. Let's get into the computer age more deeply, because this is where things get wild. The ENIAC calculation in 1949 was groundbreaking. ENIAC, Electronic Numerical Integrator and Computer, was one of the first general-purpose electronic computers. It was huge, filled an entire room, weighed 30 tons, used 18,000 vacuum tubes. Programming ENIAC was done by physically plugging cables and setting switches. It was more like rewiring a machine than writing code. And debugging was literal. Sometimes moths would get into the vacuum tubes and cause errors. That's where the term computer bug comes from. The ENIAC calculated 37 digits of pi in 70 hours. That broke Shank's record and validated that yes, Ferguson was right about where the error was. This was also important because it showed computers could be used for serious mathematical work, not just ballistics calculations and code breaking. Throughout the 50s and 60s, Computers got better and mathematicians kept calculating more digits, but they were still using variants of machine-like formulas, just automating the arithmetic. Then, in the 1970s, Richard Brent and Eugene Salamin independently discovered what's called the Gauss-Legendre algorithm, also known as the Brent-Salamin algorithm. This was different. Instead of an infinite series where you add up terms, this was an iterative algorithm where each iteration doubles the number of correct digits. So you start with an approximation, apply the algorithm once, now you've got twice as many digits. Apply it again, you double again. This quadratic convergence was way faster than even the best series formulas. It became the standard method for breaking records through the 80s and 90s. But then, in 1987, the Chudnovsky brothers found their formula, and everything changed again. The Chudnovsky formula is based on deep mathematics. It comes from the theory of modular forms and elliptic curves, topics that connect to some of the most advanced areas of modern mathematics. The formula itself has these huge numbers and complicated factorial expressions. But what makes it work is that it converges incredibly fast, 14 digits per term, and the terms can be calculated in parallel, which is perfect for modern multi-core computers. The Chudnovskys built their supercomputer in Gregory's apartment in New York. Gregory had some health issues that made it hard for him to leave home, so they built the computer there. It used multiple high-powered processors, had hard drives everywhere, and generated so much heat they had to constantly worry about cooling. They calculated over 1 billion digits, which at the time was mind-blowing, and they verified their calculation by using a completely different algorithm to check it. You calculate pi 2 different ways, and if you get the same answer, you're probably right. This verification step is crucial for record calculations, because when you're calculating trillions of digits, a single error early on can ruin everything. So you always calculate pi using at least 2 different methods and compare them. Let's talk about what it actually takes to calculate, say, 100 trillion digits of pi. First, you need storage. Each digit takes about half a byte to store in binary, so 100 trillion digits needs roughly 50 terabytes just to hold the answer. But during the calculation, you need way more. You're storing intermediate results, checksums, verification data. 100 trillion digit calculation needs hundreds of terabytes of total storage. Modern record attempts use multiple solid-state drives in parallel. You can't just use one big drive because the data needs to be read and written constantly, and you need the speed of multiple drives working together. Second, you need RAM, lots of RAM. Modern computers can have hundreds of gigabytes, even terabytes of RAM. But even that's not enough for these calculations, so you end up using swap space on the SSDs as extended memory. The computer is constantly shuffling data between RAM and drives. Third, you need a good algorithm. The Chudnovsky formula is standard, but you also need to implement it efficiently. That means using techniques like binary splitting to handle the huge numbers involved, fast Fourier transforms for multiplication, and all sorts of optimization tricks. Alexander Yi's Y-Cruncher program implements all of this and more. It's open source, which means people can look at the code, suggest improvements, find bugs. It's been refined over years to be as fast as possible. The actual computation for 100 trillion digits takes weeks or months. The computer is running continuously, grinding through the calculations. If the power goes out, if there's a hardware failure, If there's a software bug, you might have to start over. So redundancy and reliability are huge concerns. And then you have to verify the result. You use a different algorithm, often the Gauss-Legendre one, and compute pi again. If both methods agree on all the digits, you're good. If they don't, something went wrong. The 200 trillion digit record from 2024 took 85 days of calculation, plus more time for verification. That's almost 3 months of a computer running flat out, using over a petabyte of storage. Why do people keep pushing for more digits? Like, what's the actual point? Part of it is pure because it's their motivation. The same reason people climb mountains. It's a challenge, and humans like challenges. But there are legitimate scientific reasons too. One is testing computational systems. If you can calculate 200 trillion digits of pi and verify them, that means your hardware is working correctly. A single bit flip in memory, a single error in storage, and you'd get the wrong answer. So a successful pi calculation is also a validation of your entire computing system. Another is algorithm development. To calculate pi efficiently at these scales, you need to optimize everything: memory management, arithmetic operations, parallelization. The techniques developed for pi calculations often transfer to other areas of computational mathematics and science. There's also the statistical question. Is pi normal? A normal number is one where every possible finite sequence of digits appears with the expected frequency. So in a normal number, the digit 0 appears about 10% of the time, and so does 1, 2, 3, all the way to 9. More than that, the sequence 42 should appear about 1 in 10,000 times. The sequence 1, 2, 3, 4 should appear about 1 in 10,000 times. Any sequence you pick should appear with the right frequency. We strongly suspect pi is normal, but we haven't proved it. And one way to build confidence is to calculate a ton of digits and check them statistically. So far, pi passes all the tests. The digits look random and evenly distributed. But until we have a proof, we can't be certain. If pi turned out to not be normal, if some sequence appeared more or less often than expected, that would be huge news. It would mean there's some hidden structure in pi that we don't understand. It would point to deep truths about circles, mathematics, maybe even physics. So every time someone calculates more digits and they all look normal, we get a little more confident. But we're still looking for the proof. Let's talk about where pi shows up in unexpected places, because some of these are genuinely surprising. The Gaussian distribution, the normal bell curve, has pi in its formula. This is a curve that describes everything from the distribution of heights in a population to errors in measurements to stock price changes. And right there in the formula, dividing the exponent is pi. Why? Because the Gaussian distribution is derived by considering how randomly moving particles spread out in space. And space has rotational symmetry. And rotational symmetry is fundamentally connected to circles. So pi shows up. In quantum mechanics, Heisenberg's uncertainty principle has pi in it. The principle states that you can't know both the position and momentum of a particle with perfect accuracy. The product of the uncertainties has a lower bound, and that bound involves Planck's constant divided by 4 pi. Again, why pi? It's because the mathematics of quantum mechanics involves wave functions. and waves are periodic, and periodic functions are connected to circles and trigonometry, so pi appears naturally. In electromagnetism, Coulomb's law has a 4 pi in the denominator. Maxwell's equations, which describe all of classical electromagnetism, have pi showing up in various places. Same with equations for the magnetic field around a wire, the impedance of free space, all of that. The pattern is clear. Pi appears whenever you're dealing with waves, spheres, circles, or rotational symmetry, but sometimes it appears in places where the connection isn't obvious. The Basel problem, solved by Euler, asks, what's the sum of 1 over n squared for all positive integers n? 1 plus 1/4 plus 1/9 plus 1/16, and so on forever. Euler proved the answer is pi squared over 6 pi squared, from adding fractions with no obvious connection to circles. Euler's solution is beautiful and involves considering the sine function as an infinite product and doing some very clever manipulation. Or consider the Riemann zeta function, which is deeply connected to the distribution of prime numbers. The zeta function, evaluated at even integers, always involves powers of pi. There are formulas connecting the zeta function to pi in ways that seem almost magical. The Buffon's needle problem is another weird one. You take a needle of length L and drop it randomly on a floor with parallel lines spaced d apart. The probability that the needle crosses a line is 2L over pi d. You're literally dropping needles on a floor, no circles involved anywhere, and somehow pi shows up in the probability. People have actually used this to experimentally estimate pi, drop thousands of needles, count how many cross lines, do the math. It works, though it's not a very efficient method. Pi appears in the formula for the period of a simple pendulum, the time it takes to swing back and forth. It's in the equations for alternating current in electrical circuits. It's in formulas for calculating planetary orbits. The deepest reason for all of this is that pi isn't just about circles. It's about periodicity, symmetry, and the structure of space itself. Anytime you have something that repeats, that waves, that rotates, pi is likely lurking somewhere in the mathematics. The cultural impact of pi is also worth discussing. Pi Day, celebrated on March 14, has become this pop culture thing where schools do activities, people eat pie, everyone makes the same puns. It's become a way to make mathematics feel more accessible and fun. Some people complain that Pi Day trivializes mathematics, turning it into just a joke about pi. But honestly, if it gets people thinking about math for even a moment, that's probably good. There's a tradition of trying to memorize as many digits of pi as possible. The world record is over 70,000 digits, held by Rajveer Meena from India, who recited them blindfolded over about 10 hours. People use memory techniques, converting digits to words, then words to images, then constructing elaborate mental journeys through imaginary locations where each location contains a few digits. It's impressive as a feat of memory, even if it's not practically useful. There are pi digit competitions, pi recitation events, pi-themed merchandise everywhere. Pi has become the cool mathematical constant in popular culture. Part of this is because pi is easy to explain. The ratio of circumference to diameter, anyone can understand that. Compare that to e, which is the base of natural logarithms, and the limit of 1 plus 1 over n to the n as n goes to infinity, much harder to explain to a non-mathematician. Pi has also appeared in Star Trek, The Simpsons, and various other TV shows and movies. Usually, as a way to signal that a character is smart. They're reciting pi digits, or they reference pi in some clever way. There was even a movie called Pi from 1998, a psychological thriller about a mathematician looking for patterns in the stock market and descending into madness. It's a weird film, but it shows how pi has penetrated into broader culture as this symbol of mystery and mathematical obsession. Let's talk about some other interesting historical figures who worked on pi. François Viet, in the late 1500s, found the first infinite product formula for pi. Unlike the series formulas, where you add terms, Viet's formula involved multiplying fractions with nested square roots. It was beautiful, but not very practical for calculations. John Wallis, in 1655, found another infinite product, now called the Wallis product. It's pi over 2 equals 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5, and so on. Just pairs of even numbers and odd numbers multiplied together in this specific pattern. The amazing thing is that these formulas work. You can prove they converge to pi, even though there's no obvious reason why multiplying these fractions should have anything to do with circles. In the 1700s, you had Abraham Sharp using Motion's formula to calculate 72 digits. Then, in 1721, Thomas Fantet de Lagny calculated 127 digits. The record kept getting pushed higher as people found better formulas and had more patience. Zacharias Days, in the mid-1800s, was a calculating prodigy who could do complex arithmetic in his head at incredible speed. He calculated pi to 200 digits in a couple months. Days also calculated logarithm tables and did various other mathematical computations, all mentally. These calculating prodigies were valuable in the pre-computer era. Calculating things by hand was tedious and error-prone. Someone who could do it quickly and accurately was a real asset. There's also this philosophical question about pi that's kind of fascinating. Is pi discovered or invented? On one hand, pi is a property of circles. Circles exist in nature, orbits, ripples in water. The sun and moon appear circular. So pi seems like something we discovered, something that was always true whether humans existed or not. On the other hand, the concept of a perfect circle is an idealization. No physical circle is perfect. They're all slightly oval or bumpy or somehow imperfect. So maybe pi is a property of an abstract mathematical object that we invented, the perfect Platonic circle. This gets into deep philosophical waters about the nature of mathematics. Is math something we discover, like physics? Or is it something we invent, like language or games? Most mathematicians feel like they're discovering things, not inventing them. When you prove a theorem, it feels like you're uncovering a truth that was always there, not creating something new. But then again, the symbols we use, the axioms we choose to start with, the questions we decide to ask, those are human choices. Different alien civilizations might do mathematics differently. Yet somehow, it seems like they'd still find pi, because if they have the concept of a circle, they'll find this ratio. And if they do trigonometry or calculus or work with waves, pi will show up. It's hard to imagine a mathematical civilization that doesn't eventually discover pi, even if they call it something else. Let's talk about pi in the context of different number systems, because that's kind of interesting too. In base 10, pi is 3.1415926 and so on. But in other bases, it looks different. In binary, base 2, pi is 11.00100100000 and so on. Different digits, but still the same number. In hexadecimal base 16, pi is 3.243F6A88 and so on, using letters for digits above 9. But here's a cool thing. There's a formula called the Bailey-Borwein-Plouffe formula, discovered in 1995, that lets you calculate individual hexadecimal digits of pi without calculating all the previous digits. Normally, to know the billionth digit of pi, you'd have to calculate all 999,999,999 digits before it. But with the BBP formula, you can directly calculate the billionth hexadecimal digit without knowing what comes before. This seems like magic, but it works because of specific properties of the formula and how it interacts with modular arithmetic in base 16. You can't do this for decimal digits easily, or at least, we don't know a formula that works as well. This has practical applications for verification. If you calculate pi to 1,000,000,000 digits using one method, and you want to double-check just one particular digit way out at the end, you can use the BBP formula to compute just that digit and compare. If it matches, you probably didn't mess up. Now, one thing I haven't talked much about is approximate values and how different cultures handled them. The fraction 22/7 is probably the most famous approximation. It's been known for ages. Archimedes used it, and it's correct to 2 decimal places. For most everyday purposes, that's fine. 355/113, Zoo's fraction, is correct to 6 decimal places. That's way overkill for most practical applications. If you're engineering something, 3 decimal places is usually plenty. NASA uses about 15 or 16 digits of pi for interplanetary navigation. That's enough to calculate the circumference of the observable universe accurate to within an atomic diameter. Any more precision is meaningless because physical reality has limits. Quantum uncertainty, the finite speed of light, practical measurement limitations. So why does your calculator give you 10 digits of pi? Because that's more than enough for any calculation you'd reasonably do on a calculator. The extra digits are there just in case, and because memory is cheap. Why do computers calculate trillions of digits? Because they can, and because there's scientific value in testing hypotheses about pi's normality, and because computational challenges drive technological development. But for actual practical use, a few digits are fine. If you're baking a round cake and calculating how much frosting you need, pi equals 3 is close enough. If you're designing a jet engine turbine, maybe you want 6 or 8 digits, but nobody actually needs 100 digits, let alone a trillion. There are also some interesting near misses and funny coincidences with pi. Some people have proposed using tau instead of pi. Tau is 2 pi, about 6.28. The argument is that tau is actually more natural because it's the ratio of circumference to radius, not diameter. And in many formulas, you see 2 pi appearing together all the time. So why not just use one symbol for that? Tau supporters declared June 28, 6/28 as Tau Day. They argue that using tau makes many formulas simpler and more intuitive, especially in trigonometry and circular motion. But pi is so entrenched in mathematical culture that tau hasn't really caught on. Maybe in 100 years, who knows? But for now, pi is king. There's also e to the power of pi compared to pi to the power of e. Which is bigger? This is a classic puzzle. E to the power of pi is about 23.14. Pi to the power of e is about 22.46. So e to the power of pi wins, but not by much. Another fun one, pi to the power of pi to the power of pi to the power of pi, and so on forever. Does this converge to a finite value? Surprisingly, yes, it converges to about 2.48. You can calculate this by setting x equal to pi to the power of x and solving, then showing that iterating pi to the power of pi to the power of pi approaches this value. There's also the coincidence that the gravitational acceleration at Earth's surface is about 9.8 meters per second squared, which is almost exactly pi squared. This is just a coincidence. The definition of a meter is arbitrary, but it's a convenient mnemonic. Let's circle back, pun intended, to what makes pi fundamentally interesting beyond just the practical applications and record-breaking calculations. Pi is a window into the nature of mathematical truth. It's a number that we can define simply, the ratio of circumference to diameter, but which has infinite complexity. It's computable, but not constructible. It's everywhere in mathematics, but emerges from a simple geometric property. The fact that pi is transcendental means there's a fundamental limitation to what we can do with classical geometric tools. We can't square the circle because pi is the kind of number it is. This connects to bigger questions about what's possible and impossible in mathematics. The fact that we can calculate pi to trillions of digits shows the power of modern computing and algorithms. Each new record is a demonstration of human ingenuity. Better hardware, better software, better mathematical techniques all coming together. The fact that pi appears in so many different areas of mathematics and physics suggests there's a deep unity to mathematical structure. Why should the number for circles also appear in probability, quantum mechanics, number theory? Because at some level, these areas are all connected. Pi is one of the threads that tie them together, and the ongoing search for patterns in pi's digits, or the lack thereof, is about testing our understanding of randomness and mathematical structure. If pi is normal, that tells us something about the distribution of prime numbers and other number theoretic properties. If it's not normal, that would be even more interesting, because it would mean there's hidden structure we don't understand. So, where does this leave us at the end of this long journey through the history of pi? We've come from ancient civilizations estimating pi by measuring physical circles to modern supercomputers calculating trillions of digits. We've proved it's irrational and transcendental. We've connected it to physics, statistics, number theory, and basically every branch of mathematics. And yet, pi still holds mysteries. We haven't proven it's normal. We keep finding new places where it appears unexpectedly. We're still refining our algorithms and pushing the boundaries of computation. Let me tell you more about some of the modern computational achievements, because these stories are genuinely fascinating and show how far we've come. When computers first started being used for pi calculations in the late 1940s, it was seen as a way to test and validate these new machines. But it quickly became something more, a benchmark, a competition, and a scientific endeavor. In 1955, the Nork computer at the Naval Surface Warfare Center calculated 3,893 digits. The machine filled an entire room, consumed massive amounts of power, and required constant maintenance. But it showed that electronic computation was the future. Throughout the 60s and 70s, As computers got faster and memory got cheaper, the digit count kept climbing. By 1973, Zhang Yu and Martin Bouillet had calculated 1 million digits using a CDC 7600 computer. 1 million digits. That took about 23 hours of computation time and 57 hours of checking and verification. Think about that. In ancient Babylon, they had 3.125. Archimedes got to 4 decimal places. The Chinese got to 7. By the 1970s, we had 1 million. That's an insane acceleration. But the really interesting part is what happened when personal computers became available in the 1980s and 90s. Suddenly, it wasn't just big research institutions doing these calculations. Regular people with powerful PCs could attempt record-breaking computations. Yasumasa Kanada in Japan became famous for repeatedly breaking pi-digit records using progressively more powerful supercomputers at the University of Tokyo. Between 1981 and 2002, Canada's team broke the record 11 times. They went from 2 million digits in 1981 to 1.24 trillion digits in 2002. Each new record required better algorithms, better hardware, and better verification methods. Kanada didn't just calculate pi, he ran statistical analyses on the digits, checking for patterns, testing the normality hypothesis, looking for any deviation from random distribution. And here's what he found: nothing unusual. The digits looked random. 0 through 9 appeared with equal frequency. Sequences of digits appeared with the expected probability. No patterns emerged. This is actually important information. Every time we calculate more digits and they still look random, we gain more confidence that pi is indeed normal. We're stress testing the hypothesis with ever larger datasets. Then, in 2009, something interesting happened. A French software engineer named Fabrice Bellard calculated 2.7 trillion digits of pi on a single desktop computer, not a supercomputer, not a cluster, one PC. Bellard used the Chudnovsky algorithm, optimized his code extensively, and let the computer run for 131 days. He used about 1.1 terabytes of hard drive space for temporary storage and 6.7 terabytes total. This was significant because it showed that with the right optimization and enough patience, ordinary hardware could compete with supercomputers from just a few years earlier. Computing power was advancing that quickly. After Bellard came Alexander Yi and Shigeru Kondo. Kondo was a systems engineer in Japan who built custom PCs at home. Ye was a student who had written Y-Cruncher, the program that would become the standard tool for pi calculations. Together, they broke multiple records: 5 trillion digits in 2010, 10 trillion in 2011. Each time, Kondo would build a more powerful machine, more cores, more RAM, more storage, and Yi would optimize Y-Cruncher to take advantage of it. Kondo's machines were homebrew in the sense that he assembled them himself, but they were serious pieces of hardware. The 5 trillion digit machine had 2 Intel Xeon processors with 12 cores total, 96 gigabytes of RAM, and 20 external hard drives with 32 terabytes of capacity. The computation for 5 trillion digits took 90 days. The verification took an additional 20 days. That's almost 4 months of a computer running continuously, perfectly, without error. And every calculation had to be verified. You can't just trust the result. You run a completely different algorithm often the Gauss-Legendre method, and calculate pi again. If both methods give the same answer, you're probably correct. If they differ, something went wrong and you have to figure out what. The verification step is often faster than the main calculation, but it still takes days or weeks for these massive computations. And it's nerve-wracking because if the verification fails, you've potentially wasted months of computer time. In 2019, Emma Haruka Iwao, a Google employee, used Google Cloud infrastructure to calculate 31.4 trillion digits. This was notable because it used cloud computing rather than a dedicated machine. Iwao rented computing resources from Google servers, ran iCruncher across multiple virtual machines, and coordinated everything remotely. The computation took 121 days and used about 170 terabytes of data. The bill for the cloud resources was apparently around $200,000. But for Google, this was partly a demonstration of their cloud computing capabilities. Then the records started falling rapidly. Timothy Mullican calculated 50 trillion digits in 2020, running iCruncher on a single server for almost a year. 50 trillion. The 50th trillion digit is an 8, by the way, if you're curious. In 2021, the Swiss University Applied Sciences calculated 62.8 trillion digits to celebrate their birthday. In 2022, a team reached 100 trillion. The pattern was clear. With better hardware, better algorithms, and more patience, the limits kept getting pushed higher. But then in 2024, the Storage Review Lab team decided to really go for it. They used Intel Xeon 8592 Plus CPUs and solid-DIMM solid-state drives, really high-end hardware, and ran the calculation for 85 days straight. The result: 202 trillion, 112 billion, 290 million digits, over 200 trillion. To put that in perspective, if you printed all those digits in a normal size font, the printout would wrap around the Earth's equator about 2.3 million times. If you try to memorize 1 digit per second, it would take about 6.4 million years. The storage requirements were absurd. The computation used nearly 1.5 petabytes of space across 28 SSDs. A petabyte is a million gigabytes. For comparison, estimates suggest all the words ever spoken by humans throughout history could be stored in about 5 petabytes if converted to text. So this one pi calculation used nearly a third of that. And then, in April 2025, Linus Media Group and Kioxia shattered that record with 300 trillion digits. This computation took 226 days, over 7 months, and used the Chudnovsky algorithm run through iCruncher on cutting-edge hardware. 300 trillion. That's the current record, as of my knowledge. And it probably won't stand for long. Someone's already planning the next attempt. Let me tell you more about verification, because it's actually a fascinating problem in itself. When you calculate pi to hundreds of trillions of digits, you can't just trust that your computer did everything right. Hardware can fail, software can have bugs, cosmic rays can flip bits in memory. All sorts of things can go wrong. So you verify by calculating pi a second time using a completely different algorithm. The Chudnovsky algorithm is usually the primary method because it's fast. For verification, people often use the Gauss-Legendre algorithm or one of its variants. But here's the thing, you can't just compare the final answers. You have to compare at multiple checkpoints throughout the computation, because if there's an error early on, it will propagate through all subsequent calculations. So, you might calculate the first trillion digits with both methods and compare them, then the next trillion, and so on. This way, if there's a mismatch, you know roughly where the error occurred. Modern pi calculations also use checksums and error detection codes. The data is stored with redundancy so that bit flips or storage errors can be detected and corrected. It's similar to the error correction codes used on CDs and DVDs. There's also the Bailey-Borwein-Plouffe formula, which lets you spot check individual hexadecimal digits without calculating everything before them. So, after calculating all 200 trillion digits, you might use the BBP formula to verify a few specific digits way out at the end. If they match, that's additional confidence that the calculation was correct. All of this verification adds significant time to the computation. For the 200 trillion digit record, the main calculation took about 85 days, but verification and additional checks added more time on top of that. Let's talk more about how pi has permeated popular culture, because it's actually pretty widespread. Pi has appeared in literature. In Carl Sagan's novel, Contact, the protagonist discovers a message hidden deep in the digits of pi. At a certain point, the digits form a pattern that encodes a circle in binary. This is fiction, of course. In reality, no such pattern has been found, and most mathematicians doubt one exists, but it made for a great plot point about messages from the universe. The number 42 from The Hitchhiker's Guide to the Galaxy by Douglas Adams is often compared to pi as a number with seemingly cosmic significance. Fans search for 42 in pi's digits, and of course, it appears many times because pi contains everything if you look long enough. There's a genre of poetry called pillish, where the number of letters in each word corresponds to the digits of pi. The Cadaic Cadenza by Mike Keith is a long pillish poem that encodes the first 3,900 digits of pi. Each word has a number of letters matching the next digit. The first sentence, not a nasty, dirty, wet hole. That's 314159 letters, respectively. It's a neat trick and requires significant creativity to make the text readable while matching pi's digits. Musicians have tried to turn pi into music by assigning notes to digits. 0 might be C, 1 might be D, and so on. When you play pi, you get a sequence of notes with no obvious pattern. Some people find it interesting or even pleasant. Others think it's just random noise. Either way, it's a fun experiment. There's been pi-themed art where the digits are color-coded or arranged in patterns. Some artists create visualizations of pi, like spirals where the color changes based on the digits. None of this reveals any hidden structure in pi, but it looks cool. Pi has appeared in countless movies and TV shows. In Star Trek, Spock once defeated a computer by asking it to compute pi to the last digit, which is impossible since pi has no last digit. The computer presumably exploded or froze or something. The Simpsons, known for sneaking in math references, has shown pi multiple times. There's an episode where a blackboard shows an approximation of pi, and another where Homer Simpson appears to solve Fermat's last theorem, though the numbers shown actually don't work if you check them carefully. The movie Life of Pi isn't really about the number, but people made the connection. The protagonist's full name is Piscine Molitor Patel, shortened to Pi. He explains early in the movie that he's named after a swimming pool, but prefers Pi to his full name. And, of course, there was that 1998 movie actually called Pi, a black and white psychological thriller where a mathematician becomes obsessed with finding patterns in numbers, particularly pi. He believes there's a hidden code that will predict the stock market. It's dark and surreal, and it uses pi as a symbol of mathematical obsession and the search for meaning in chaos. Here's something worth explaining in more detail. Why is pi about 3.14 specifically? Like, why not 2.7 or 5.8 or some other number? The answer comes from the relationship between a circle's diameter and circumference. If you have a circle with a diameter of 1 unit, the circumference is about 3.14 units. So the circumference is roughly 3 times the diameter, but a bit more. Why is that? Well, think about it geometrically. If you take the diameter and lay it along the circumference, you can fit it about 3 times with some left over. The first diameter takes you about a third of the way around. The second takes you 2/3. The third takes you almost all the way around, but not quite. You need another 14% or so of the diameter to complete the circle. That extra bit, the 0.14 and all the digits after, is what makes pi irrational and interesting. If circles were such that the circumference was exactly 3 times the diameter, pi would just be 3, and geometry would be simpler but less beautiful. You can also think about it in terms of polygons. A hexagon inscribed in a circle has a perimeter that's exactly 3 times the diameter of the circle. So if pi were 3, circles would be the same as hexagons. But circles are rounder than hexagons. They curve more smoothly, so their circumference is a bit longer. Hence pi is more than 3. As you increase the number of sides of the polygon, the perimeter gets closer to the circumference. An octagon gets you closer than a hexagon. A 12-sided polygon closer still. By the time you're at 96 sides, like Archimedes calculated, you're very close to the true value. The limiting value, as the number of sides goes to infinity, is pi. It has to be some specific number, because geometry is consistent. And that number turns out to be 3.1415926, and so on forever. Let's talk about the connection between pi and e, because they show up together all the time in mathematics, and there are some beautiful relationships between them. First, Euler's formula, e to the power of I times pi equals -1. This is often called the most beautiful equation in mathematics because it connects 5 of the most important mathematical constants, e, I, pi, 1, and 0. Why does this work? It comes from the Taylor series expansions of e to the x, sine, and cosine. When you plug in I times pi, the exponential series becomes a combination of sine and cosine series, which evaluate to -1. But beyond the formula itself, pi and e are related in deeper ways. They're both transcendental numbers. They both appear in countless formulas throughout mathematics, and often they appear together in the Gaussian integral, the area under the bell curve. You integrate e to the -x² from -infinity to +infinity, and the answer is the square root of pi. Why does pi show up when integrating an exponential function? Because the derivation involves polar coordinates, which bring in circles, which bring in pi. In Stirling's approximation for factorials, n factorial is approximately the square root of 2 pi n times n over e to the n. There's pi and e together again. In the Riemann zeta function, zeta of 2 equals pi squared over 6. Zeta of 4 involves pi to the 4th. Even zeta functions evaluated at other points have pi in them. The gamma function which extends the factorial to non-integer values, has pi in its functional equation. The probability density function for the normal distribution has e and pi together in the formula. It's as if these two numbers are dance partners in the mathematics of the universe. Wherever one appears, the other is likely nearby. And they are connected through deep relationships that hint at some underlying unity in mathematical structure. Here's something interesting. Pi generalizes to higher dimensions in ways that are both intuitive and surprising. In 2 dimensions, pi is about circles. The circumference is 2 pi r. The area is pi r squared. In 3 dimensions, we're talking about spheres. The surface area of a sphere is 4 pi r squared. The volume is 4/3 pi r cubed. Pi is still there, but now with different coefficients. In 4 dimensions, and yes, mathematics can deal with 4 and higher dimensional spaces, even if we can't visualize them. There are hyperspheres. The volume of a 4-dimensional hypersphere involves pi squared. Specifically, it's pi squared times r to the 4th divided by 2. As you go to higher dimensions, the formulas involve higher powers of pi. An n-dimensional hypersphere's volume involves pi to the power of n over 2, along with factorials and other terms. But here's the weird part. As dimensions increase, the proportion of the hypersphere's volume concentrated near its surface increases. In really high dimensions, almost all the volume is in a thin shell near the surface. The center is proportionally tiny. This has implications for things like high-dimensional geometry and statistics. It's one reason why high-dimensional spaces behave counterintuitively, and pi is right there in the formulas describing all of it. Let's dig into some philosophical questions about pi, because they're genuinely interesting. Is pi real? That might sound like a weird question, but think about it. Pi is defined as a ratio of measurements of a perfect circle, but perfect circles don't exist in physical reality. Every physical circle is made of atoms, which are discrete, not continuous. Even a circle drawn by the most precise machine has imperfections at the atomic level. So in what sense does pi exist? It exists as a mathematical object, certainly. We can define it, calculate it, prove theorems about it, but it's not a physical object you can point to. This connects to a big debate in philosophy of mathematics. Platonism versus formalism versus constructivism. Platonists believe mathematical objects exist in some abstract realm. Pi is real in the same way that the form of a circle is real in Plato's theory of forms. When we do mathematics, we're discovering truths about these abstract objects. Formalists believe mathematics is just a formal game with symbols. Pi is a symbol that behaves according to certain rules. It's not real in any deep sense. It's just part of a consistent symbol system. Constructivists believe mathematical objects only exist insofar as we can construct them. Pi exists because we can compute its digits, prove theorems about it, and so on. But we can only talk about the parts we can actually construct or compute. Most working mathematicians are Platonists in practice, even if they're not philosophically committed to it. It just feels like we're discovering things, not inventing them. When Euler proved that the sum of 1 over n squared equals pi squared over 6, it felt like uncovering a truth that was always there, not creating something new. But that intuition isn't a proof. The philosophy of mathematics remains contentious, with smart people arguing for different positions. Here's a fun thought experiment. Imagine an alternate universe where circles work differently and pi equals exactly 3 or 4 or some other simple number. If pi were exactly 3, hexagons and circles would be the same shape in some sense. The most efficient packing of objects might be different. Ball bearings would roll differently. Wheels might not work as smoothly. Architecture would change. Domes and arches rely on circular geometry. If circles had different properties, the structural engineering would be different. Some buildings that are stable in our universe might not work in that one. Music would be different. Sound waves are periodic, and periodicity involves circles and trig functions, which involve pi. If pi had a different value, the mathematics of harmonics and resonance would change. Musical instruments would produce different overtone series. Quantum mechanics might work differently. The wave functions that describe particles involve complex exponentials and trigonometric functions. These are intimately connected to pi. Change pi, and you change the fundamental equations of quantum mechanics. Of course, this is all wild speculation. The value of pi follows necessarily from the definition of a circle in Euclidean geometry. You can't change it without changing the fundamental axioms of geometry itself. And if you change those axioms, you're not really in a different universe, you're just doing a different kind of geometry. Non-Euclidean geometries exist, spaces with positive or negative curvature where the rules are different. On the surface of a sphere, for instance, the ratio of circumference to diameter depends on the size of the circle. Small circles approach pi, but large circles can be quite different. In hyperbolic geometry, on a saddle-shaped surface, the ratio is always greater than pi. The circumference grows faster than linear with the diameter. So, in a sense, pi is specific to flat Euclidean space. Other geometries have different constants. But in our universe, space appears to be very nearly Euclidean on everyday scales, so pi is the number we use. Even after centuries of study and trillions of calculated digits, we're still looking for patterns in pi, or rather, looking to confirm there aren't any. Statistical tests have been run on pi's digits countless times. Every test shows they're consistent with randomness. No bias toward any particular digit. No sequences that appear more or less often than expected. No autocorrelation. Knowing one digit doesn't help you predict the next one, but statistical tests can only give you confidence, not proof. There could be a pattern that emerges at the quadrillionth digit or the googolth digit or somewhere we haven't reached yet. The question of whether pi is normal, whether every finite sequence appears with the expected frequency, remains open. We believe it's true, the evidence supports it, but we don't have a proof. Proving normality is hard. It requires showing that pi has a specific kind of randomness, that its digits are generated by a process without bias or pattern. And that's tricky when pi is defined by a geometric property, not a random process. Some numbers are known to be normal. The Champernowne constant 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just writing out all the natural numbers in order is provably normal, but its construction is explicitly designed to be normal. Pi's digits emerge from the geometry of circles. There's no obvious reason they should be evenly distributed, yet they appear to be. That suggests something deep about the connection between geometry and number theory. If someone proved pi is normal, that would be huge news. it would be a major result in number theory. But if someone proved pi is not normal, if they found a bias or pattern, that would be even bigger news. It would suggest there's hidden structure in circles that we don't understand. So the search continues. Every new record calculation is also a test of normality. So far, pi keeps passing. But we keep looking because mathematics is about proof, not just evidence. Where does pi computation go from here? We've reached 300 trillion digits. Will we hit a quadrillion? 10 quadrillion? The main limitations are hardware and time. Computing power keeps improving, but not as fast as it used to. Moore's law, the doubling of transistors every 2 years, is slowing down. We're reaching physical limits of silicon-based computing. Future records will likely require either massive parallelization, coordinating hundreds or thousands of computers working together, or new computational paradigms like quantum computing. Quantum computers are particularly interesting because they operate on different principles than classical computers. They use quantum superposition and entanglement to perform certain calculations much faster than classical computers can. Could a quantum computer calculate pi faster? It's not clear. Pi calculation is mostly about arithmetic, adding, multiplying, taking square roots. Quantum computers aren't necessarily faster at arithmetic. They're faster at specific tasks like factoring large numbers or searching unsorted databases. But maybe there's a quantum algorithm for pi that we haven't discovered yet. Or maybe quantum computers will just help with the verification step, cross-checking classical calculations faster. Another possibility is specialized hardware. Just like Bitcoin mining led to specialized chips called ASICs, maybe someone will design chips specifically optimized for pi calculation. Chips that can do the specific arithmetic operations required by the Chudnovsky algorithm as efficiently as possible. Or maybe the future is in algorithms, not hardware. Maybe someone will discover a new formula for pi that converges even faster than Chudnovsky. Maybe there's a breakthrough waiting that will obsolete all current methods. What's certain is that people will keep trying. As long as there are computers and mathematicians, someone will want to calculate more digits of pi. It's a challenge, a benchmark, and a window into mathematical truth. Let me take some time to explain some of the mathematics behind pi in more depth, because understanding how these formulas work makes the story even more interesting. When Archimedes used his polygon method, here's what he was actually doing mathematically. Start with a hexagon inscribed in a circle of radius 1. Each side of the hexagon has length 1, so the perimeter is 6. The circumference of the circle is 2 pi, so this gives you a lower bound. 2 pi is greater than 6, or pi is greater than 3. Now for the circumscribed hexagon, one drawn outside the circle where each side is tangent to it. The perimeter of this hexagon is 4 times the square root of 3, which is about 6.93. So 2 pi is less than 6.93, or pi is less than 3.46. Now you double the sides. For a 12-sided polygon, you can use the half-angle formulas from trigonometry. If you know the side length of an n-sided polygon, you can calculate the side length of a 2 n-sided polygon using the Pythagorean theorem and some clever geometric tricks. The formula Archimedes used essentially says, if d sub n is the side length of an n-sided polygon, then d sub 2n squared equals 2 minus the square root of 4 minus d sub n squared. You start with d6 equals 1 for the hexagon, then recursively calculate D12, D24, D48, and D96. Each time you double the sides, the perimeter gets closer to the true circumference, and you're approaching pi from both above and below, squeezing it into a tighter and tighter range. Liu Hui's innovation was to work with areas instead of perimeters, and to recognize that the error decreases by roughly a factor of 4 each time. So, if you know the area of a 96-sided polygon, you can estimate the area of a 192-sided polygon without actually calculating it. Then, extrapolate to the limiting value. This is an early example of Richardson extrapolation, a technique for accelerating the convergence of a sequence. Modern numerical analysts use similar ideas all the time. Now let's talk about infinite series. The Leibniz series says pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7, and so on. Why does this work? It comes from the Taylor series for arctangent. The arctangent function has the series expansion arctan of x equals x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. This series converges for x between -1 and 1 inclusive. When you plug in x equals 1, you get arctan of 1 equals 1 minus 1/3 plus 1/5 minus 1/7. But arctan of 1 is pi over 4. Because the arctangent of 1 is 45 degrees, and 45 degrees is 1/4 of 180 degrees, which is pi radians. So pi over 4 equals the series. The problem is that this series converges very slowly. At x equals 1, you're right at the edge of the convergence interval, so convergence is as slow as possible. To get even 10 accurate digits, you'd need thousands of terms. Machin's formula is clever because it uses the arctangent addition formula. The formula states that arctan of A plus arctan of B equals arctan of the quantity A plus B over 1 minus AB, provided AB is less than 1. Through some algebraic manipulation, you can show that pi over 4 equals 4 times arctan of 1/5 minus arctan of 1 over 239. Now you're evaluating the arctangent series at 1/5 and at 1 over 239, much smaller values than 1. The series converge much faster there. At x equals 1/5, the terms decrease by a factor of about 25 each time. At x equals 1 over 239, they decrease by a factor of about 57,000 each time. This is why a machine could get 100 digits using this formula in the 1700s. The Chudnovsky algorithm is even more sophisticated. It's based on Ramanujan's work on modular forms and elliptic functions. Without getting too deep into the technical details, because that would require a whole other video, the idea is that certain modular forms have Fourier expansions, where the coefficients are related to pi. Ramanujan found formulas like 1 over pi equals the square root of 8 over 990 squared times the sum from k equals 0 to infinity of a particular expression involving factorials and the number k. The Chudnovsky formula takes this idea and optimizes it. Each term involves factorials of 6k, 3k, and k, along with some specific numerical constants. When you add up these terms, you get an expression that equals 1 over pi. The key is that the terms decrease incredibly fast. The ratio of consecutive terms approaches about -1 divided by a huge number, around 640,000 cubed. So each term is roughly 50 billion times smaller than the previous one. This is why you get 14 digits per term. Log base 10 of 50 billion is about 10.7, but the convergence is even slightly better than that pure ratio would suggest, giving you the full 14 digits. Computing each term is expensive. You're calculating factorials of huge numbers, raising 640,000 to large powers, doing divisions with massive integers. But the payoff is worth it, because you need so few terms to calculate a billion digits. You only need about 71 million terms. Compare that to the Leibniz series, where you'd need on the order of 10 billion terms to get a billion digits. The computational savings is enormous. Let's explore some of the physics connections in more detail. In quantum mechanics, pi appears in the Schrödinger equation, which describes how quantum systems evolve over time. The equation involves the second derivative of the wave function, and when you solve it for simple systems like a particle in a box, pi shows up in the energy eigenvalues. For a particle in a one-dimensional box of length L, the allowed energy levels are n squared times h squared over 8mL squared, where n is a positive integer, h is Planck's constant, and m is the mass. Wait, where's pi? Well, often Planck's constant is written as h bar, which equals h divided by 2 pi. So the energy levels actually have pi buried in the constant. The reason is that h bar is the natural unit for angular momentum in quantum mechanics, and angular momentum involves rotation, which involves circles, which involves pi. In electromagnetism, pi appears in Coulomb's law. The force between two charges is proportional to the product of the charges divided by the square of the distance, all divided by 4 pi times the permittivity of free space. Why 4 pi? It's because of the geometry of three-dimensional space. The electric field from a point charge spreads out equally in all directions. The area of a sphere of radius r is 4 pi r squared. So the field strength decreases as 1 over 4 pi r squared to conserve the total flux through any sphere surrounding the charge. In general relativity, Einstein's field equations relate the curvature of spacetime to the distribution of matter and energy. The equations have pi in them because you're integrating over volumes in spacetime, and volumes involve factors of pi. In statistical mechanics, the partition function for a system often involves integrals over position and momentum space. These integrals, especially for systems with rotational symmetry, bring in factors of pi. The cosmic microwave background radiation, the afterglow of the Big Bang, has a blackbody spectrum. The formula for blackbody radiation, derived by Planck, involves pi. The total energy radiated is proportional to the fourth power of temperature, with a constant of proportionality that includes pi. Pi is woven throughout physics because physics describes reality, and reality has circles, spheres, waves, and rotational symmetry. You can't escape pi when you're describing the universe. For all the theoretical beauty, let's not forget that pi has real practical uses. Engineers use pi constantly. Designing anything circular, wheels, gears, pipes, tanks, bearings, requires pi. The formula for the volume of a cylinder is pi r squared h. If you're designing a fuel tank, you need to know its volume. That means you need pi. In construction, arches and domes use circular geometry. The Romans built aqueducts with arches, and they needed to calculate the curve accurately. Modern architects designing domed stadiums or curved buildings use pi in their calculations. In manufacturing, anything that involves rotation uses pi. The relationship between linear speed and angular speed is linear speed equals angular speed times radius. If a wheel is spinning at a certain number of revolutions per minute, and you want to know the linear speed of its edge, you need pi. GPS satellites orbit the Earth, and their orbits are basically circles or ellipses, which also involve pi. Calculating orbital mechanics requires pi. The period of a circular orbit depends on the radius and involves pi in the formula. In medicine, MRI machines use magnetic fields that rotate. The frequencies involved are calculated using pi. CAT scans reconstruct three-dimensional images from two-dimensional slices, and the mathematics involves Fourier transforms, which involve pi. In communications, radio waves have frequency and wavelength, related by the equation frequency times wavelength equals the speed of light. When you're working with antennas, the wavelength determines the antenna size, and quarter wavelength or half wavelength antennas are common. If you want an antenna for a specific frequency, you calculate the wavelength using pi. In music, the overtone series of an instrument is determined by standing waves. The wavelengths of these standing waves involve fractions like 1/2, 1/3, 1/4 of the fundamental wavelength. The frequencies are related by simple ratios, but when you're calculating the actual frequencies from physical dimensions of the instrument, pi comes in. Even in finance, pi appears. The Black-Scholes equation for option pricing involves the normal distribution, which has pi in it. When financial analysts calculate the probability of certain price movements, they're using statistics that involve pi. So while calculating trillions of digits is more about pushing boundaries than practical need, pi itself is incredibly practical. We use it every day in countless applications, usually with just a few digits, but it's essential to modern technology and engineering. I want to end by talking about why pi is beautiful, beyond just being useful or interesting. There's a concept in mathematics called elegance. An elegant proof or formula is one that achieves a lot with simple means. It's clear, it's powerful, and it has an aesthetic quality that mathematicians recognize. Pi is elegant because it's a single number that captures so much. It's the ratio for all circles, the period of trigonometric functions, the constant in the Gaussian distribution, the connection between the circumference and area of a circle, and countless other things. Euler's formula, e to the I pi equals -1, is elegant because it connects 5 fundamental constants in one simple equation. When you first see it, it seems almost miraculous. Why should these particular numbers be related in exactly this way? The answer is that they're all aspects of the same underlying mathematical structure. Complex analysis, Taylor series, trigonometry, they're all pieces of a unified whole. Pi is one of the threads that ties them together. There's also beauty in the questions about pi that remain open. The normality question is beautiful because it asks about the relationship between geometry and randomness. If pi is normal, that connects the deterministic world of geometry to the probabilistic world of statistics in a deep way. The appearance of pi in unexpected places is beautiful because it suggests that mathematics is more unified than it appears. When pi shows up in number theory or quantum mechanics or probability. It's a clue that these areas are connected underneath, and there's beauty in the human story. From Archimedes scratching diagrams in the sand, to Zhu Chongji laying out counting rods, to Madhava discovering infinite series, to modern computers calculating trillions of digits, it's a story of human curiosity and persistence spanning millennia. Each generation built on what came before. Each breakthrough made the next one possible. And it's not over. We're still learning about pi. We're still finding new connections, new applications, new mysteries. That ongoing journey is beautiful. The fact that after 4,000 years, we're still discovering new things about something as simple as the ratio of a circle's circumference to its diameter, that tells you something profound about mathematics and about human curiosity. That's pi. From 3.125 in ancient Babylon to 300 trillion digits in modern data centers. From Archimedes' polygons to Madhava's infinite series to the Chudnovsky algorithm, from a practical measurement for building grain silos to a fundamental constant appearing throughout physics and mathematics. It's a number that's simultaneously simple and infinitely complex, a ratio anyone can understand, yet a value no one can fully capture, a property of circles that somehow connects to waves, probabilities, quantum mechanics, and the distribution of prime numbers. The story of pi is the story of mathematics itself, humanity's ongoing attempt to understand the structure of reality through logic, calculation, and proof. Every culture that developed mathematics found pi. Every generation pushed the understanding further, and the journey continues. We're still calculating new digits, still testing for patterns, still finding new places where pi appears. After 4,000 years, pi still has secrets to reveal. That's what makes it beautiful. That's what keeps mathematicians coming back to it. That's why pi will continue to fascinate people for as long as humans study mathematics. 3.141592653589793 and on into infinity, forever beckoning us to understand a little more, calculate a little further, discover a little deeper. That's pi, and that's why it matters.